Because you might see big matrices, let me explain how to find the characteristic polynomial in a quicker way. So here's a big matrix that a computer will easily do. So people will never do it in life. But it's good to know what's at the back. You know, you might write algorithms for Microsoft. I'm not sure if in Amazon you can unionize. So how do you find it? You do minus lambda, right? Right? And you have to compute this the determinant. So before you instead of doing row reduction, we might as well do 2 to 3 stuff. So what was the goal in row reduction? In other words, independent. Sure, yeah, but how does the matrix look like at the end? Yeah, but often what you want is just arbitrary, because then the determinant is just the product of the diagonals. So here you have a 9, and that's a 9. So you swap. So you have 9 minus 1 minus lambda, 0, 0, and 5 minus lambda minus 1, 0, 0. And now you want to kill that guy, because you want to make it arbitrary. Well, so first I swap row 1, row 2. And the reason I do is that I cannot divide by 5 minus lambda because it could be 0. Yeah, which I mean, it could be, it won't be. Yeah, it's a polynomial, can have any value. All right, so then you multiply the top row by lambda minus 5. And you divide, and you subtract, if you add it, plus row 2, right? So I'm just going to do the first row just to give you the idea. Then, yeah, so the guy is still the same, but you just killed the, yeah, you killed that, right? It's 0. And then this guy was minus 1, and now it will be plus minus 1 minus lambda times lambda minus 5. Oh, yeah, you have to divide by 9. So then, I know it looks terrible, but I mean, was there a better way to do this? Yeah, there's no better way. So, Anyway, so the point is now you have, at least on the top upper triangular, so let me do the other one. So same thing, you have, yeah, that's fine. And now the next guy, you do row 3, row 4, you change them. So you have 12 minus 3 minus lambda, 7 minus lambda minus 2, 0, 0, 0, 0, right? And now you want to kill this guy. So you do lambda minus 7 over 12 times row 3 plus row 4. And so that becomes 0, 0. Yeah, this guy doesn't change. 0, 0, 0 minus 2 plus lambda minus 7, 12 times minus 2. Okay? I mean, it's disgusting, but at least you don't have to do row reduction. Yes? Mistake? Oh, it was 3 minus lambda. Yeah, thank you. No, but the matrix would be much easier. Oh, I see. You have to find the eigenvalues. I don't know what you're comfortable with. I make more mistakes with this than with cofactor, because cofactor it's just 2 by 2. So like 2 by 2, 2 by 2. Here I have to like keep track of numbers, and it still might not work. Like you might still get like this is an ugly factor. Anyway, so I just wanted to show you that you can do it with 2, 2, 3. Okay, you don't need cofactor expression. Because I know you haven't done it, that's why I'm saying. Some of you have not seen cofactor. All right, so let me briefly review what happened, because we haven't finished this. We found the eigenvalues, and by reading the multiplicity, you can get the size of the table, all right, of the Jordan block, same thing. So since it is 2, you get that the first block will be size 2 by 2, okay? And the other 2 will be 1 and 3, but again, 1 by 1, 1 by 1. Right. So when they ask you for Jordan canonical form, you write down the matrices in any order you like, it doesn't matter. And then you write down the in like symbolic form. So this is called canonical. Okay, this is called Jordan canonical form. All right. Question? Oh, you can't see? Can you see now? It is paused. This is garbage. Trash. Trash. Again. Okay, we'll see. I mean, you can tell me if it doesn't work. Right. Okay. Right. So when they ask you for Jordan canonical form, please do not write the huge matrices. Write the blocks and put them. You won't have space. All right. So what else did we talk about? Yeah, let me repeat a little bit. So we talked about finding eigenvectors and that was just, let's say for this guy, you write down your matrix, and then you have x1, x2, x3, x4 equal to 0, right? And then you get a 3 by 3 system, 3 by 4, and you got these solutions. So you got 0, 0, and then 1, 3. Okay? Right. So that was finding the eigenvector. And then you compare, and you see that the eigenspace is generated by one guy, but multiplicity is 2, so your matrix is not what? Huh? Yeah, it's not diagonalizable because E2 is strictly less than M2. Okay, so be able to do this on the fly. And that means you're missing a vector. And right, but at least you can write down the blocks. So let me explain what happened here. Let me come back to it. So you have 3 blocks, and we talked about, and the question was, do you put a 1 or star? Well, if M2 was equal to E2, then the question mark is 0. But M2 is strictly bigger than E2, so you put a 1. Yeah, because we're doing Jordan canonical form. So it's either 1 or 0. 1 or 0. 0, if it's all zeros, you're diagonal, isomorph, and then if not, you put a 1. Okay, so you don't need any more information than just eigenvalues. Yeah, you don't need the full system. You don't need to know like to solve all the eigenvectors. At the same time-wise, like I'm trying to find the fastest way. So you play around and you decide. But here you don't need the eigenvectors. You just need to know that it's not diagonalizable. Because if it is, you put a 0. That's all you need. But they will ask you another question to find it. So let me do that again, just to refresh, make sure we're on the same page. So the eigenvectors, you find them like I did before. You have a system, right? So I think I did it here, right? I found one of the eigenvectors. So it looks scary, but it's a 3 by 3 system, right? So yeah. So what is it? You have like 5 minus 1. Let's do the minus 3. Minus 3, and then minus 1, 9, minus 1, minus 7 minus 3, minus 2, 12, minus 3, minus 3, and this whole guy by x1, x2, x3, x4. And what is that? This is like 2 minus 1, 9, minus 4, 4 minus 2, 12, minus 6. And you get what? Some terrible system. 2x1 minus x2 is 0. 9x1 minus 4x2 is also 0. 7, no, what am I here? 4x3 minus 2x4 is 0. 12x3 minus 0. And you get contradictions, right? So like the x1, x2 becomes 0 because you can just do like 4 times. So you have 9x1 minus 8x1 and equal to 0, right? Right? So you get x1 is 0. Because I saw that they differ by 4. So I multiply by minus 4. But then the x3 guy, they're the same. So you get 2x3 equal to x4. And so you have 0, 0, 2, 1, 2. Okay? That's it. Let's go and find eigenvectors, okay? Let's go back. I know it's terrible, but I don't know any faster way. So yeah, that was one of the guys. And what else do we want to? So you have your eigenvectors. Now you want to find your generalized eigenvector. And all you do is you have to solve the following system. So you find, so it was number 2. So this guy, right? This guy over here had it was an E2. How do I call this? I have all these different names. This is V2. Okay, good thing I have names. Right, so now you want to solve the following system. So A minus 2I x1, x2, x equal to 1, 3, 0, 0. And the reason you do that is because if you take power twice, you get A minus 2I V2, which is 2v2 minus 2v2, right? So x is a generalized eigenvector. That's the logic behind this. Okay, right. And I mean, I don't want to write all this matrix again, but you will get a system from here, okay? Okay. If you want me to do it this time, we will do it for other examples. And if you do it, you get the answer 1/3 0, 0, 0. Questions? Okay. Yeah, we talked about this, so that's why I like finding the characteristic polynomial, because from here you can read off the size. So for lambda equal 1, you just have one box because multiplicity is 1. You have k1 dimension is 1, so only one box, right? Okay. Same thing for 3, and here you have lambda minus 2 is squared, so dimension of k2 is 2. So you have two boxes, but then let me ask you again, will it be like this, or will it be like this? Which one is it? Right. Nobody do this. So is it this or this? Yeah. This or this? What's the vote? Oh, this way? Huh? Yeah, we talked about it yesterday. You know that, yeah, yesterday. So how do you find the number of boxes on the column? first column. What's the first? What? How can you get the number of columns in the first? The number of boxes in the first column. Yeah, I see your hand. Yeah, thank you, Sakura. So the number of boxes is on the first column is kernel of n. In general, when they ask you for the jth, so if you see some line of like the signature, the jth column is ding kernel of nj minus kernel of nj minus 1. And the first one will just be kernel of n. And we found this. It was just E2, right? So it was 1. So you have 1 box. That's one way to see it. There's multiple proofs. Another proof is that the nilpotency degree was 2. So a minus 2i squared restricted to the space blah 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 is 0. So you have 2 like this. How else? We also had an element in the kernel of n squared. So we had kernel of n squared, which is E2, sorry, K2. Yeah, so that's another way to see it. So we have K2 minus E2, and that was also 1. So you have a box over here. Okay? Right? Because the number of boxes in kernel of n squared are second column minus plus first. And so this guy was 2. Yeah, whatever, you get the point. And this one was 1. Okay, you can tell me if you don't get it. But there's multiple ways to get the table. Make sure you are comfortable. All right. Yeah, so we're doing now. Let me do some more problems and then we'll come back. Sorry. I don't know. I was going to ask you what you guys want. No, topic-wise, yeah, there's nothing else. Let me first do the problems, and then we'll do a review, and then on Friday, we'll continue with review of the entire course. All right? Okay. So they give you a signature, 1, 2, 3, 4, and I want you to tell me how I can go from here to here, and from here to here. So why can I go from here to this table? So how do I come here? So let me remind you signature. So signature of the Nilpotent map is what is it? Kernel of n, kernel of n squared, all the way to the kernel of the nilpotence called k. All right, and the number of elements is equal to the how many, like the nilpotency degree. So anyways, I want to say, yeah, how can I get this table? What do you think? Yes. Can you speak up? Yeah, so perfect. So the way you find each of the columns is you play this calculus game. So you want to find number of boxes on the first. So you have one. You want to find on the second. Uh, it will be uh, yeah, kernel of n squared minus kernel of n. So 2 minus 1. Uh, yeah, yeah, and then one more. So the easiest thing to first do is find the uh, of kernel of n, because then it will tell you how many rows you have, right? Um, but anyways, so yeah, exactly that's what happens. So we simply look at the right. So okay, how about the matrix? How do I go from the table to the matrix? Where you get the table, the matrix. Huh? What do you think? Do you know? Yeah, that's why I want to see. Okay. So you're playing on your phone. That's your solution. Does anybody know how to get the matrix? All right. Let's see. So um, so the way we do this is with cycles. All right. So if you have an important map, so you have some important n important. You first form the cycles, right? So we have this basis of n m1 v1 v1 union lm2 v2 and so on down to let's say vl, right? So these were your cycles, and each of the cycles we put them in the tableau, right? So I drew this picture. Uh, I had, let's do it like this. So I had v1 dot 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 nm1 v1 and v2 dot 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 nm2 v2 v3 and then eventually vl just vl minus 1 and vl and then just vl. All right, but then you already have the tableau, and you know the tableau is only one row, right? So we have this information which tells us that we only have only one cycle. Is that okay? But then, how do you form the blocks? You formed a block for each of the cycles. Why? Because this became your basis, right? So you had the first columns were n of the first cycle, second was n of the second cycle, and eventually n of VL, right? That's how you get your columns. And each of them gave you a block. Okay? So now, how many blocks do you have? Show me with your finger. Cursor. So the reason there's only one is because you only have one row, so you have one cycle. So then in the Jordan block, you only have only one Jordan block. And Jordan blocks are always of the same form, just 0 and then 1 on top. That's called a Jordan block. Okay? Yeah. So then, yeah, we're looking at Nilpotent maps here. So let me make those prints. So yeah, so we got our table is one row, so you only have V1 all the way to N3 V1. So you only have you have 4 elements, so it will be 4 by 4. Okay. And yeah, you have your 0 column, 0 row, and then 1, 2, and then this guy, and that guy. And if you want me, I can tell you how you find this. So you do here n of n cubed V1, which is 0, n of n squared V1, which is n cubed V1, so you get a 1. And then n of n V1, which is n squared V1, so you get here. And then n of V1, which is a 1 over here. Okay. Questions? If it's one row, it means we only have one Jordan block. That's right. And the block will be 4 by 4 because it has 4 blocks in the row. Right. So the size of the blocks is the dimension for your it's the nilpotency degree, and it gives you the dimension for your eigenspace. So there's many ways to see this. Sure. So yeah, like you can see it here. You have 4. The signature has size 4, and you get a 4. If it was 1, 2, 4, what's the nilpotency? Yeah, it would be 3 blocks, and it would be a 3 by 3 matrix. It would be actually I should do this. No, just a second. So no, there's no such thing. What do I want to do? Now I want to do the 1, 2, 4. That's a good one. Well, let me do my examples. We'll come back. Okay, fine. Let me do the 1, 2, 4. It's a nice example. So just a second. So let's do this. Sometimes these signatures they're not actual signatures of an important map. Remember in your homework, yeah. So I don't know if this has so let's be careful here. I don't think this one has. Yeah, it doesn't. Can you tell me why it doesn't correspond to an important map? That's a good question. Yeah, but there's a quick proof with boxes and Young Tableaus. So no not nilpotent map. Why? There's a quick proof using our machinery. Yes. Can you speak up? Yeah, so that's pictorial, but can you give me the kernel argument? What's the kernel? No, it's one. Oh yeah. So yeah. Oh, you mean no? You're talking about. Okay, so this is kernel of n, right? This is kernel of n squared, and you mean the third column, kernel of n cubed, right? Right. So if this was a valid Nilpotent map, you will have one, another one, but then you will have to make a jump, right? And this is not a valid from our results. Like they have decreasing lengths. Okay, so what's another way to say this? No. This is not a valid Young Tableau. No, just a second. Let me think. So, what do I want to say here? I want to say. N cube is 4. Nilpotent C is 3. And then what are we saying? That it jumped by 2? Yeah, what do you think? Why is it not valid? Yeah, go ahead.
So they're not equal.
And then why is it the image?
Oh, okay. Dimension of image of x squared is like 4 minus the dimension of the kernel, because the dimension of the subspace is 4, so it's 4 minus 2. The dimension of the image of x squared is 2, but the dimension of the image of x squared is also supposed to be the dimension of kernel of n, because like n cubed is 0. So that we already know the dimension of kernel of n is 1, so it's like it's saying it's both 1 and 2, so it's possible.
All right, let me see. Yeah, that's one way to do it. That's right. So, no, but okay. So a quick way to see this from this tableau, because we have the result that they have to be decreasing lengths. Okay, this one says that you have like another 2 blocks like this. Yeah, they have to be decreasing length. No, but this guy over here is not in the kernel of n, which is basically what you said. Yeah, the columns. Yeah, that's another way to see it. And so the problem here is exactly what you were saying. So here you have kernel of n cubed, take away, kernel of n is two-dimensional, right? And no, it's two. And no, I mean the square here is. Or you can do this way as well. Yes. So that means there are two vectors that do not correspond to the kernel of n. So you can do it this way as well, if you like. So you have 3. So first row has first column has fewer elements than last column, which is a contradiction. I mean, like that's the quickest way because the way we arrange those cycles are so that the first column has all the elements in the kernel. I mean, I can go through all the proofs. Okay, I mean, but let's do it. Okay, let me do it differently. So you want a randomly. Because we built all this machinery, so I don't have to do this. So, all right. What's another thing? So kernel of n. Kernel of n contains kernel of n squared. Do we agree on this? Just a second. Do we agree on this? Because you guys are disputing on the size of the column. Yeah. So the size of a column of kernel of n is what? Oh, what am I doing here? No, you're right. What do I want to do here? Oh no, I know what I want to do. Sorry. So I want the complement, and it was so one of the elements that are not equal to 0, but n squared of v is 0, right? So you have nv is some w. So yeah, let me do it that way. So you have all the guys that are not in the kernel, right? And yeah, even from here you have problems. So let's do the kernel n cubed, and we have kernel n squared. I remember proving this, the conclusion. So then, yeah, this guy was 4. And what did we have? This guy was a 2, right? And this. So what do we want to say? That's because I haven't done this example and it came out of nowhere.
Like that's 2, but it's also kernel of n, which is 1. So that's another.
Why is even to n squared kernel of n?
Because n cubed is 0. So
no, n cubed is not 0. N cubed. Yeah, this is the whole space. That has nothing to do with kernel of n. Yes, and?
like n times like n of n squared of anything is 0.
Oh, I see.
Like n of n squared of b is 0.
Let me
so
see.
n squared of b is
yeah, sure. Image of n squared. Yeah, but that doesn't tell you that they're equal.
no, I'm just saying what the image of n squared has dimension 2, but the kernel of n has dimension 1. So
No, it doesn't. Kernel of n cubed is 4. Yeah, but image of n squared is not in the kernel of n. Oh, I see what you're saying. Wow, yeah, I'm making a lot of stupid mistakes. Thank you. Now I understand. Yes, that's right. Yes, so this guy is n squared w. So then we have nv. That's right. I see. Okay, now I understand. Thank you. And then we got this guy. I thought we had it proved that we have these things. I guess that's why, but yeah, please don't do these things because in a way we have all these results encoded in the tableau, right? So it's a lot of work for you to work through all these dimensions. Yeah, we like, you know what, on Friday, I should, because I thought we had this. Didn't we have this? I remember we talked about this, but it was like in the proofs, so it's kind of digged inside. But yes, so I will try, on Friday, I will just state the result, give you the short proof for this column thing, so that you don't have to work with kernels and stuff like that. Yeah, because this is, I got lost. All right. So, okay, now let's do this guy. So again, you have 3 boxes on kernel of n. Then you have 2 in the second column, right? Right? So you have 3 plus 2 is 5. And then you have 1 more and 1 more. So this is the tableau. And then can you tell me what's the matrix? How many blocks do I have? Let's do this one by one. How many blocks? Can you show me with your hand? How many blocks do you think? So we have 3 cycles, 3 blocks. Okay, so 3 cycles, 3 blocks, and that's it. And it will be 4 by 4, and 2 by 2, and 1 by 1. So you have 1, 2, 3, 4. Then you have 2 by 2, so you just put a 1, and then you have a 0. Okay? Ah, I knew I had this 1, 2, 4 question. But my argument was with decreasing row columns. So I should give you the, I thought I had this result. Okay. All right, let's do, yeah, it's the same stuff. So I thought I had a nice proof for this. So the same problem, you have, the moment you fix the first row, first column to be 1 box, you're trapped. Because now you have to put 2 boxes like this, and then 1 box like this. And this is not a valid Young Tableau. They have to be columns of decreasing length. And what? No, I will give you the on Friday. I thought I had this result proven, but I guess I haven't. So I will have to. So okay, this is saying. So let's do this. So now in reverse, you should be able to do that as well. We give you the matrix and find the table. First, find the blocks. So what are the blocks on this matrix? What are the Jordan blocks? Or let me ask you this: how many Jordan blocks are there? Do it with your hand. How many do you think? How many do you see? So what is a Jordan block? Jordan block is something that goes like this: 0, 1, 0, 0. How many zeros you like? But you must always have a 1 on top. Right? So how many blocks do you think we have? Well, it would be so there's one guy, and then like this. Because you if it was a big, it will have to be 0, 1, 0, 1, 0, 1, 0. Right? Okay, we'll continue operating.
Yes, this is no something.